In this video, we're just going to recall some basics of decidability and undecidability. So, what we want to remember is that we have this idea of a reduction. So, what we mean is if A reduces to B, we can use a solution to B solve A. Okay, in terms of the languages we are dealing with that are sets of strings, sets of problems, what we mean is that if I have some decider for B and I can reduce A to B, then I can put the problem I'm trying to solve in A, the language I'm trying to decide in A. I can either convert it somehow or otherwise run the decider for B, and any answer I get from B I can apply to A. Okay, and then in the rest of our videos we're going to actually show examples of doing this. So this is just the basic idea. What this also gives us some information about decidability and undecidability. So if A reduces to B and B is decidable, then A is decidable. Okay, to realize that this is true, if I know that I can convert the problem A into an instance of the problem B, then if I can decide that instance of the problem B, I'm really deciding the problem A. Okay, so if I can reduce A to B and I know B is decidable, then I can decide A. Conversely, if A reduces to B and A is undecidable, then B cannot be decidable. Okay, why is this? If I know that A absolutely is undecidable, it cannot be decided, and I can reduce A to B, if I had a decider for B, I could decide A, but we know A is undecidable. Therefore, a decider for B cannot exist. Otherwise, we'd have a contradiction. Okay? Something to note is that we don't have anything that says this. If A reduces to B and A is decidable. I'm not even going to finish the statement because it's going to be false. So, okay, we can't say anything about B. Knowing that I can convert a problem, an instance of a problem A into an instance of a problem B, and I can decide the instance of the problem A, it doesn't actually tell me anything about B in general. Okay, I cannot say that B must always be decidable. It's not true. Okay? All this is saying, really, is that A can't be harder to solve than B. Okay, if A reduces to B and B is decidable, B is solvable, A can't be undecidable. A must also be decidable. A can't be harder than B. Here, saying A can't be harder than B and A is decidable doesn't tell me that B can't be undecidable. B could be harder than A to solve. It just says A can't be harder than B. Okay, so this is an important distinction. How do we use this? There's two basics for decidability. Okay, so if you're trying to prove that A is decidable, there's a couple ways to do it, but one way is to find some decidable B that A can be reduced to. So what do I mean? If A reduces to B and B is decidable, A must be decidable. So if I can find some B that's decidable and that A is reducible to, then I can conclude that A is decidable. Okay, so that's usually the easiest way to prove decidability. Another way is just to construct a Turing machine that decides the problem. Sometimes this is easy with, say, regular languages. It might be pretty easy to say, here's a Turing machine that always halts on every input. Well, actually, that's a really difficult statement to say. So you might be able to find a DFA that solves that problem. Okay. But if you can't, you can just find some other decidable language that you can reduce this language to. Okay, so then for, I can't spell this word today, undecidability. Okay, so if I want to prove that B is undecidable, how do I do this? We do a proof by contradiction. Okay, so what we're going to do is we're going to find some A that is undecidable and reduces to B. Next, we suppose that B is decidable. Okay, and then we arrive at a contradiction. Okay, why? If A is undecidable and it reduces to B, if we assume that B is decidable, then we can use the decider for B to decide A. But we know A is undecidable. This gives us our contradiction. Okay, so this is the basic format for a proof of undecidability. Okay, something that you can't do when you're trying to prove undecidability. Okay, so don't do this. How do I want to say this? Don't attempt to find a TM that fails to decide B. Okay, so this seems pretty obvious, but sometimes we're tempted to say, well, I can construct this Turing machine and it's going to accept, you know, the input, the strings that should be candidates for the language of B, and then maybe go on to show that that machine runs forever and therefore it's not a decider. Okay, why does this not work? I can make any machine run forever. All right, I can construct a Turing machine that will loop on any input. Just because some machine runs forever on some of the inputs that should be in B doesn't mean that every machine will. Okay, so this is some basic discrete math principles that if you want to prove that something does not exist, you can't just give an example and show that it doesn't work. You have to show that there is no possible way to do this. Okay, so the way that we do this is by this kind of structured proof by contradiction. Okay.